Good morning, everyone. My name is Daryl Hurwitz, and this is my thesis presentation of what I've worked on over the last year. And it was in collaboration with the Vitale lab and my research advisor, Michelle Johnson. And so the title of my thesis is Rapid Fabrication of Patient-Specific High-Density Microelectrode Arrays. And as an overview, according to Goosh in 2011, nearly 100 million Americans were affected by at least one or more than the 1,000 neurological disorders. This translates to an overall cost of $765 billion for the more prevalent conditions, including Alzheimer's disease and other dementias, chronic lower back pain, stroke, migraine, epilepsy, and traumatic brain injury, and Parkinson's. At that time, during the study, there was no comprehensive report on neurological disorders for the United States. That changed in 2020. The U.S. Neurological Disorder Collaborators published the burden of neurological disorders across the U.S. from 1990 to 2017, comparing Goosh's study and the study produced by Berlongen indicated that there was nearly 200 million Americans that were affected by at least one neurological disorder, ranging from the attention type headache and migraine to stroke and dementia. The Institute of Health Metrics and Evaluation further evaluated this report in the Global Health and Data Exchange in 2019 that 1 in 8 people globally, that's 1.01 billion people, were living with some type of mental disorder, with anxiety and depression disorders being the most common. The WHO reports that there's over 50 million people who are affected by epilepsy, with the average cost per person in the United States ranging from $1,022 to $19,749 per person. And this is not as much as Parkinson's disease is a little bit lower in that range. In 2017, the disease affects 1.04 million people, individuals, and was estimated to cost $52 billion a year. So the cost associated is significantly more than those of epilepsy. There are multiple methods of treatment for conditions, including medication, invasive and non-invasive surgery. For instance, in relationship to epilepsy medication, although they do not cure epilepsy, they can effectively reduce seizures up to 6% in patients. With the remaining 40%, surgical intervention is needed. However, surgical treatment for epilepsy has been the most underutilized of all proven effective therapeutic interventions in the field of medicine. This is because the success of surgical resection depends on the accuracy identification of the seizure onset zone. And it is often very difficult to characterize epileptic activity of the brain and identify appropriate resections regions with sufficient accuracy to proceed with surgery. The efficacy of these methods could be significantly enhanced by improving the temporal and spatial resolution of the imaging and monitoring techniques. Higher resolution would allow for a more precise mapping of epileptic activity, leading to improved outcomes in surgical interventions by targeting one of the critical areas involved in seizure generation. Moreover, the advancements in brain-computer interfaces and robotics are opening new possibilities for treatment conditions like paralysis. BCIs can enable communication and control for patients who are paralyzed by translating the neural activity into command to operate. New technology in prosthetics. This technology not only assists in communication, but also enhances the mobility through advanced robotics, which can be integrated into exoskeletons and other assisted devices. These devices offer a non-pharmacological and non-surgical route to rehabilitation, providing a significant quality of life improvement for individuals and severe mobility impairments. Enhanced temporal and spatial resolution and BCIs would further refine those interactions between the neural pathways and robotic responses. So when designing and fabricating bioelectronic interfaces, such as BCIs, there are some basic guidelines through some universal principles, including low interfacial impedance and intimate integration with soft and curvilinear tissues. If there's a mismatch between those biological tissues and the electrodes, they can elicit various adverse biomechanical interaction, including scar tissue formation from the body's immunoresponse system. Such adverse biomechanical interactions can increase interfacial impedance and distance between the electrode and target cells. As you can see, it's not as clear as it is on my screen. On the left, you can see that there is angular interaction with the devices, depending on if they match the mechanical and electrical properties of the device itself. The performance and efficacy of the bioelectronic stimulation and recording. At the epidermal interfaces, human skin is both stretchable and breathable, but electronics are typically not stretchable and require impermeable encapsulation for prolonged lifetimes. And so one of the resolutions is using two-dimensional materials such as Maxines, and they're an innovational two-dimensional material developed over at Drexel University by Dr. Ugorvi, derived from max phase by selecting and etching the elements to expose layers of transition metals, combined with a carbon or nitrogen atom, which gives them the name Maxine. These surfaces terminated with functional groups like the hydroxyl, oxo, fluoryl, and chloral groups, which enhances their diverse properties. Maxines also exhibit excellent electrochemical, chemical, mechanical, optical, and magnetic characteristics, making them highly tunable and suitable for a range of applications. However, they face challenges such as susceptibility to oxidation, which is prevalent in biological systems. The versatility extends to high conductivity, significant electrochemical capacitance, robust mechanical strength, and potential and transparent coating and spin products. Driven by ongoing advancements to overcome stability issues and broaden their practical issues, there have been multiple methods proposed to improving its properties, with one being the functionalization of Maxines with polydopamine. Now, polydopamine-based materials have been drawing inspiration from natural occurring melanin, like muscles, since they gained prominence in 2007, particularly in fields regarding high biocompatibility. These materials are extensively studied for the non-toxic nature across various cell types, including cancer cells. Also exhibit enhanced cell adhesion and proliferation on different substrates. This has broadened their applicability in biomedical engineering by improving antibacterial and anti-inflammatory properties, which is one of the predominant reasons why they want to use it in brain-computer interfaces, or at least I decided to use it in my thesis. Conversely, Maxines, through their advantageous in electronic performance, suffers from mechanical fragility when processing into films and rapid degradation under ambient conditions. Typically, that is what we notice as oxidation of the two-dimensional material mixing. And so this approach enhances the mechanical and environmental stability of MaxSeam films without significantly impacting their electrical conductivity. So by functionalizing MaxSeams with polydopamine, the treatment increases tensile strength and ductility while providing an effective barrier against oxidation of moisture, which is crucial for applications requiring durability and reliability. And this in the bottom, as it is clearer on my presentation screen, this is the proposed mechanics of introducing dopamine with the self-polymerization of MaxSeam. And so these improvements have made MaxSeam films more versatile for other applications, such as storage capacity for batteries and sensing uranium for cleanup approaches when designing devices. So in terms of fabrication methods for the electrodes, there are many electronic printing fabrication methods, such as deposition, optical lithography, screen printing, direct writing, etc., commonly performed in the Singh Center here at Penn. As one of the main purposes for this thesis was to develop a fabrication process which could allow rapid fabrication of patient-specific electrodes. The traditional method of optical lithography, which can take days and require specialized masks, is subject to manufacturing lead times. It is both time-consuming and costly. To address these challenges, my research has concentrated on direct ink writing, specifically inkjet printing with the Dymatics DMP 2850 and extrusion-based robocasting. I'm sure many of you have heard of 3D printing or additive manufacturing. This is just a two-dimensional landscape for your FDM process. Each one of these methods offers distinct advantages in terms of resolution, accuracy, and cost effectiveness. But due to time constraints, this presentation, I've removed the inkjet portion, as the end results weren't as efficient as the ones with extrusion-based robocasting techniques. So utilizing the Vitale V1, which optimized the production process of custom designed electrodes, significantly reducing overhead costs and fabrication. So whenever you've developed a electrode, you're wanting to deal with the characterization of those electrodes. There are three main analyses conducted with respect to electrochemistry: electrochemical impedance spectroscopy, cyclic voltammetry, and voltage transients. In electrochemical impedance spectroscopy analysis, the response of electrode to a harmonic perturbation, typically is a sinusoidal signal at a given frequency. The amplitude of this harmonic excitation signal must be low, between 10 and 100 millivolts, to prevent undesired irreversible chemical changes at the phase boundaries. In short, the microelectrode to be characterized as immersed in electrolyte solution, typically PBS, because that's is the closest solution to our body's chemical makeup. And so it's put in with the working electrode, counter electrode, and the reference electrode. And there's a linear response that is crucial. It's in the yellow zone right over here, the intermediate. And this is crucial for accurately interpreting the impedance data to understand the electrochemical processes occurring at the electrode interface. EIS conveniently decouples the performance of an electrode surface from the other components influencing the performance of the neural interface. It facilitates a standardized comparison. This connection between the expected high signal to noise ratio recordings and low impedance is instead theoretically grounded in the physical contribution to the noise at the recording electrode, which is thermal noise. And then while conducting voltage transient analysis, the current passes over a solid liquid boundary of an electrode. It faces several challenges. The interface plays a crucial role in transitioning electronic charges, carries from the solid electrode to ionic movements in the biological fluid. This mechanism is crucial for understanding how electrodes interact with biological systems. They can be reversible or irreversible, impacting the electrode's ability to return to its original state after stimulation. In terms of neural stimulation, this charge is typically a biphasic charge balance signal. This approach involves reversing the polarity halfway through the stimulation, aiming to maintain a net zero charge. Ideally, an electrode should handle infinite simulation pulses without an altering its state. However, the dynamics are more complex and charge balance may be achieved through different processes. As for this reaction, we're looking for a Faradic reaction at a threshold in which all the electrodes would generate such a reaction. If the threshold is within the water window limit, that's when your water molecules are breaking up and going into an oxidation state and separating and creating hydrogen and oxygen, which in terms is electrolysis, which damages electrodes and is harmful for surrounding tissues, which evidently would kill the patient. And then finally, when using cyclic voltammetry, it is particularly useful for analyzing Faradic reactions and their dependence on various parameters like pH, diffusion, and concentration. And so it's critical for estimating the charge storage capacity of electrodes, which represents total charge transferred during a cyclic sweep and incorporating all charges regardless of their mechanism. The method is particularly emphasized in neural interfacing, focusing on the cathodic charge storage capacity as a comparative measure among electrodes. However, it's important to recognize that only a fraction of the charge outlined by cyclic voltammetry is actually available for short pulse injections. And so here's where I get into the ink formulation with the rheological results in comparison to my PDA Maxine. As we can see, all of the compositions, whether it's PVA, addition of ethanol, or just straight Maxine, it lies in the superimposed area of the extrusion printing and dry spinning. When comparing the viscosities of 36 milligrams per milliliter, the zero shear viscosity of the Maxine PDA ink is remarkably higher at 396 pascals seconds compared to the Maxine ink at 159. So the Maxine PDA ink possesses substantially higher frequency independent storage modulus and loss modulus, indicating primarily solid like behavior in the formation of pseudo-solid networks. And so in the top right, we approximate those regimes, like I stated, and it is beneficial for extrusion printing. The bottom left, we have an analytical examination of the rheological properties delineated by the Herschel-Buckley model. Yes.
5 minutes.
Oh, 5 minutes. And with this shear thickening, it presents that it may require substantial pressure to initiate flow. And then here we have the comparative study of the relationship between layer thickness and conductivity of the MaxCine and MaxCine PDA on various substrates using linear and quadratic regression analysis. The analysis showed that the quadratic regression models, which reflect non-linear relationship between the number of layers and conductivity, better than the linear models. Overall, in terms of the different substrates, ETFE perform better than polyamide and PET, which is typically used for substrates, for flexible substrates. And with these findings, we find that the optimal layering for desired conductivity is around 3 to 5 layers for MaxCine PDA and ETFE combination. Further analysis with the surface topology comparison through visual observations with SEM imaging, we can see the surface deposited MaxCine ink is rougher than that of the MaxCine PDA ink. And then using atomic force microscopy, the RMS roughness of the MaxCine PDA ink is 19.7 nanometers, indicating that the flakes are in alignment, more so than that of the MaxCine ink. Next, we have the fabrication methods using the Volterra V1 with enhanced. Using the Volterra V1, we can see that here's the scheme for fabricating the individual MaxCine PDA electrodes. You have the option of doing multi-layer, which is the high-density electrodes. We have to add additional substrates, which is the ETFE, in between the encapsulation layer, which is PDMS. And here we have the 3 characterization rays for testing the Volterra V1, showing the capabilities and dimensions of each. As we can see, as the complexity of the device increases, the total time increases as well, with the encapsulation time included with the total time. In the top right is the standard design, and the bottom right is the high density electrodes, and they are interspaced by 50 microns. Okay, so in terms of simulation recording metrics, given my previous explanation of characterization metrics, for the standard 2.5, at a frequency of 1 kilohertz, we're getting a 68.92 ohms with a standard deviation 21.21 ohms. When compared to similar size electrodes, the impedance is 4 times less than the standard platinum and 3 times less than the previous studies of MaxCine. For the microcontacts at 250 microns, at 1 kilohertz is 295 ohms. Compared to similar electrodes, 6 times smaller than the platinum and 5 times smaller than the gold. Unfortunately, there's no comparable size from MaxCine in previous studies. This information indicates, given the lower impedance and lower signal-to-noise ratio, is for their respective composition. On the next slide, we have the voltage transients. And as we can see, if we recalled from the data on the left, the total charge storage capacity for contacts at 50 millivolts per second with the respective water window refills, enhanced capacitive charge and charge delivery for the MaxCine PDA with approximately 4 times larger than the platinum electrodes. And other common materials such as platinum, iridium, and composites, and PDOT-PSS, which is the competitive material. For time, we also have the achieving long-term stability. And that is it. Fortunately,
Go ahead and just wrap up because we can take a little bit of your.
so achieving long-term stability and thin film neural electrodes is essential that we establish chronic stability. And here we have our long-term stability test, which uses a second-order exponential decay model. The analysis revealed that while Maxine exhibited rapid material degradation with high initial charge storage, Maxine PDA incorporated a uniform decay constant, lower amplitude than that of the Maxine, indicating that it has a better chronic stability window than Maxine does. And then in future work, in improvements, there's a need for further characterization of the electrodes, optimization of the Maxine PDA formalization, and then further modifications beyond the Volterra V1 that I conducted but did not include into this presentation, and then continued fabrication of the ACF bonder for intermediate connections. Any questions? I know that's a lot.
I know. So this would actually be considered like bioadhesive, right? And so when you talk about long-term, what do you mean by? Does it mean like the life cycles that you have?
In terms of chronic implementation. So if you want a device in for longer than a week, a month, etc., that's the stability window that we're looking at.
And that's assuming that it's actually continuously delivering these electrical.
And that data that I showed right here showed that over about 29 days, there's a continuous transmission of